Right, welcome everyone to the Mornington Peninsula Astronomical Society. And I'll begin first of all with a couple of minutes taken from the ABC News website about the Blue Origin launch a couple of days ago on the 15th of April.
First all-female spaceflight in more than 60 years has successfully returned to Earth after a brief journey.
Start, 2, 1, ignition. Liftoff.
The crew, which included American pop star Katy Perry and Lauren Sanchez, the fiancée of billionaire Jeff Bezos, spent about 10 minutes in space aboard the Blue Origin capsule. The crew reached an elevation of over 100 kilometres in the unpiloted capsule before landing safely in West Texas. Katy Perry, who sang the song What a Wonderful World during the trip, says she was thrilled to be part of the historic launch.
This experience is second to being a mom.
We weren't just taking up space, we were making space for the future. And for me, like Gail said, this wasn't a ride, it wasn't a destination, it was a journey, and it was a supernatural one.
Owner Jeff Bezos hugged his emotional fiancée just moments after the capsule landed. She says it was a profound experience.
I don't cry that often, so I didn't expect to be this emotional, but it's also all the love that was in that capsule and all the heart and the feelings and all the things, and like seeing Jeff before I left, I just went, you know.
So they basically went up to 100 kilometres, which is the Kármán line. So strictly speaking, yes, they were in outer space, or they touched outer space very, very briefly. Suborbital flight, so in other words, they didn't go into orbit. They didn't go once away around the world at least. As was pointed out on this one, it's the first time an all-female flight since the first woman in space, which was the Russian Valentina Tereshkova. In 1963 was also an all-female crew, because she was the only one on the crew, so by definition is also all-female. In this particular one, you see the 6 of them on the top right-hand side there of the screen. The actual cost of the tickets hasn't been revealed, other than the fact that the down deposit had to be about 300,000 Australian dollars just to get just to get a shoe in the door, and then I think it goes almost to a bit of an auction as well. So the price can vary anywhere from 0 up to $50 million, which is Australian dollars. So on average, the tickets tend to come out at around $30 million each. So as I think Katy Perry pointed out in another interview, she recommends this for everyone. I think I must be missing out on something there. So anyway, they gave that a 10 out of 10, and they survived the experience. And I'd have to say, when you see the Blue Origin launches, they just seem to be so effortless getting off the ground, whereas when you see the SpaceX launches, they seem to be quite ferocious engines getting it off the ground in comparison to this one. Down in the bottom left-hand side there, the White House nominee for heading up NASA is due to be appointed in just under 2 weeks' time, and he's another billionaire. This time he's at least been in outer space very, very briefly. He was one of the only civilians to ever do a very brief spacewalk, I believe, so at least he's got some connection with outer space. And his view on the matter is that we shouldn't be going to the moon and then to Mars. We either do it in parallel, or we skip the moon and throw away the Artemis missions and just basically try for Mars up front. So no surprise there that probably Elon Musk has had some influence there, and you might find a lot of NASA programs cut as a result of that, with funding redirected elsewhere, would be my guess. On the bottom right-hand side there, recently announced that a binary system of 2 white dwarf stars. A white dwarf is what our sun will become in its dying throes after it turns into a planetary nebula. But 2 of these in orbit about each other have been found only 150 light years away, which is relatively close in the northern hemisphere, the northern constellation of Hercules. And they're only about 1/60th the Earth-Sun distance apart. So they're relatively close to each other and spiralling slowly inwards. And when they do collide, they will turn into a Type 1a supernova. And when that happens, they will flare up to be very, very bright. And the best estimate they got at such a close distance of only 150 light years away is it will be magnitude -16, plus or minus a few magnitudes. Which will make it a lot brighter than even a full moon, but not quite as bright as the sun in the sky, or at least they certainly would hope not, because that could be rather disastrous if that occurred. In their last couple of minutes, this is what the simulation shows. You could probably see the little counter at the top of the video as it goes. That's a number of seconds ticking by. And it doesn't take too many seconds once they get to this sort of distance to go kaboom. No sound on this one from the Nature Astronomy paper, but you can see what is happening there. Starts ripping material off the other one, and then all of a sudden, about 2 minutes after they've approached, kaboom. And we'll get a flash in the sky 150 years later. Now that could occur any time, they said, in the next 23 billion years. So it's not going to occur probably in our lifetime. Although they're relatively close, those 2 suns to each other, they are quite stable, so it's going to take a long time to shed energy to pull themselves in. But will be spectacular at the time. Okay, welcome everybody to tonight's meeting, and especially to any new members. We don't have a list of new members tonight, and I know we have one new one here, and you've already spoken to Nerida, our new members officer, so you've picked the right person up front. So welcome this evening, and make yourselves at home, and please everyone make a welcome if you have a break for tea a little bit later. As usual, I'll talk about the events past month and coming month, then I'll throw over to Chris for Astromofo and Guido for Sky for the month. Then we'll look at some astronomical spectroscopy. This is looking at not so much stars, but the stuff in between the stars. So the clouds of material in between, how do they know what's in it? And there are 3 spectroscopists of various flavours there who will give a bit of a talk about spectroscopy. And then at the end we'll close with actually a really wonderful video showing the scale of things. I'm not sure if anyone has ever remembered this Scientific American publication called Powers of 10 by Morrison and Morrison. It was very, very well known back in the late 1980s. And it basically does a very, very similar thing to what this West Australian astrophysicist has actually done with what I close tonight, and a lovely finish to the evening it will be. Okay, so recent events, we've had a few. At the top there we had a public night in collaboration with the ASV way out at Inverloch, which is an unusually long distance to go, and overall there was about 300 public for the 2 nights there. Simultaneously with that we had the Telescope Learning Day here at the Briars and the buy-sell swap, and shown on the top right hand side there is Rod Brackenridge and some of the car boots full of stuff for sale, junk there, and overall the buy-sell swap was a big success, and we'll indeed have it with the next TLD as well, so we'll have another one when that one comes around. We ended up with 80 visitors there, and thankfully no cloud at all that night, which was very, very good. Makes a change from some of the past TLDs. We then had a committee meeting, and we've got some constitution changes which will have to be rushed through to look after the tax changes that the ATO has imposed on all incorporated societies. Obviously, there are some people out there who have been misusing incorporation to try and pass assets onto themselves, and if you don't actually make some basic changes to your constitution, the ATO will deem you to be eligible for paying income tax on everything that you have, every income from various sources outside and inside sources as well. Now, normally incorporated societies are not for profit, and so we don't pay income tax. We've always been exempt. But if you take no action, then you automatically, by default, become taxpayers the same as everyone else. And we obviously don't want to do that. So we're looking at the changes that are necessary for that, which will probably be pushed through in the next month or two. So if you have an email come round to Scorpius about that, just be aware that that's what this is all about and what it's being driven by. We also talked about security here on the site during public nights. On the 28th of March, we were due to have one of our skag nights for the Scouts, Cubs and Guides, but that was cancelled because we didn't have enough bookings, so gave up on that. 28th of March, there was a star party down at Glenaladale, and that was not sort of an outreach night as such, but a regular star party, not so much for the public, but more for members of societies down with the Latrobe Valley Astronomical Society and the ASV as well. 4th of April was another successful public night, apart from the 90% cloud. Nevertheless, people did get to see plenty of things in the night sky, believe it or not. But 90% averaged across the evening, but when it was time to come out, they all got a good clear view, which was really, really fortunate. Then on the 11th of April, we had the Red Church youth group who were staying at the camp next door to us. They came over, and they were basically high school level students, and you can see a snapshot there at the bottom right that Phil took, and you can see all the girls were sitting on the left-hand side of the room and all the boys were sitting on the right-hand side of the room. And you'll notice I'm standing over on the left-hand side, and Catherine's over on the other side. And I could have messed with their minds and swapped positions with Catherine. It would have been interesting to see whether or not they also swapped sides of the room as well. But they all had a great time, and 0% cloud. So coming up soon, we've got the Working Bee this Saturday, as usual, with the members' night afterwards. So beginning at 4 p.m. with the Working Bee, and then the barbecue a little bit later. 22nd of April is a committee meeting by Zoom, which I think is Tuesday. Cosmology Discovery Group, the next one up here is on Saturday the 26th of April, so not this Saturday, the following Saturday. So as far as I know, that one is still going ahead in the Saturday afternoon. The next public night on the 2nd of May will also have a visit from a small men's club called the Men of Glen Burton's Club, which is coming down as well. And Trevor Hand will give that talk, given that he's now back in the country. 5th of May and 7th of May, we've got 2 nights for Mornington Primary School for Year 3-4 pupils. They're also staying next door on camp, I think, on those 2 nights. And we've had them in previous years as well. And then the next meeting here is on the 21st of May.
Welcome to AstroMofo number 23, our monthly photo challenge. And the last one was Carina, the Carina constellation, which rounds out our tour of Argo Navis. So the 2 previous challenges were Vela, the sail of the Argo Navis, Pupus, the poop deck, and now we have just done Carina. So Carina is actually the hull, or literally it translates from Latin as the keel of the ship. And if you were outside now at the moment, you would be able to see the Southern Cross pretty much around about there. And if you look to the right of the Southern Cross, that's where you see Carina, and it stretches all the way across to the bright star Canopus, which is the second brightest star in the sky. So that's where Eta Carina is, and Canopus is pretty much the rudder or the steering oar of the ship, and Canopus is actually the name of the navigator of the Spartan king Menelaus when he went to Troy to try and take back Helen. So that's Eta Carina. Canopus, by the way, is around about 310 light years, which is sort of relatively close. It's a white giant, which is why we see it as so bright. The first brightest star in the sky is Sirius, of course, and that's only about 8 light years away. So that sort of gives you an indication of the actual difference between the two stars. Sirius is sort of a solar mass star, or thereabouts. Canopus is a white giant, much further away, but much brighter, so they appear similar in the sky. Okay, we had quite a few contributors this challenge, and several new photographers as well. This was completed by Isaac Markowski, Dennis Cook, Michael Barrow, Sylvie Grandit, Greg Walton, Guido Tack, Kelly Clitheroe, Liam Laub, Maya Trichek, Nick Axaris, and Chris Kostokanellis. And this image here was taken by young Isaac Markowski down at the here at the Briars during the telescope learning day with his refractor, and some help from Greg Walton as well to get this really nice image of Eta Carina. So well done to Isaac, and also to the other first timers, Maya, first image from Maya, and I think Dennis as well. We got a Eta Carina from Dennis too, so well done to those. Okay, first photo, we're looking at this wide field shot. This is from my backyard, taken with a Sigma 10 to 20 millimeter lens on my Astro camera. And this is at 14 millimeters. Stopped down to f4, and what stopping it down does is it pretty much helps the stars around the edge to stay pinpoint rather than to flare out and become seagulls. That you do tend to get a bit of seagulling effect on the stars with a wide field lens, especially if you don't have the backspacing right. But stopping it down a little bit is a bit of a trick to help keep them pinpoint. So this was 17 2-minute exposures. I would have liked to have taken more, but the trees started getting in the way, as you can see in the bottom right-hand corner there. Now you can see, where are we? Okay, actually I'll use this one, this is better. Well, it's not better. Nope. Anyway, I'll use this one. Okay, here we have the running chicken nebula. So if we were to go a little bit further out this way, this is where the crux would be. Then we have the running chicken nebula here, Eta Carina, the southern Pleiades over here, and there's quite a lot going on. We've got quite a few images around this part of the sky here. We've got the southern beehive cluster down here, Canopus down here, and what I might actually do is, hang on, that. Back. Okay. Southern beehive, Canopus down here, and over here we've got the gum nebula. So Carina, the hull stretches across this part of the sky down here, down to Canopus. So this is the bow of the vessel going down to the rudder or the steering oar down here at Canopus. Up here is where we have Vela, and around the back here is where we have Puppis. And over here, these stars here are the back legs and the tail of Canis Major, the big dog. Okay, next we've got this shot here by Sylvie Grandit with with her Red Cat 51. So 76 frames, 300 seconds, and a really nice wide field of view with that telescope. Red because what we're seeing with the red is hydrogen alpha emissions, which glow red. And that's why a lot of these nebulas, and particularly Eta Carina, has a lot of red in it because it is an emission nebula. So Eta Carina is around about 8,500 light years away, and from edge to edge the nebula is around about 460 light years across. Kelly Clitheroe got this one with a sea star, which is a mosaic image. So she's taken a few different, blended them together to get a wider field of view than you would normally get with a sea star. And what we're starting to see, these images here will sort of zoom in a little bit as we go, so they'll get tighter and tighter. But we're starting to, let's go back. We're starting to get a little bit, this is the Gabriela Mistral Nebula here, and the gem cluster just, the gem cluster just up there. And then as we're getting in closer, this is by Guido Tack, a really beautiful image. Well done, Guido. we're starting to make out the Keyhole Nebula in Carina. And the Keyhole Nebula is that, keeps doing that. The Keyhole Nebula is this feature over here next to the star Eta Carina from where the nebula takes its name. So this is by Guido with the L Extreme filter, 29 5-minute exposures processed in Pix Insight. So really nice shot there. This one also by a new member, Maya Tricek, I believe that's how you say it. And this was also imaged here at the Briars on one of the nights that Greg had the observatory open, and I'm pretty sure this was through the refractor with her Nikon D90. So really, I wish my first image of Eta Carina looked this good, but really well done. And Dennis got this one here as well through the 8-inch Newtonian. So well done, Dennis, down here at the observatory. And you're able to see the Keyhole Nebula a little bit clearer in this one as well. And you're also, this is where Eta Carina, the star Eta Carina is. The Keyhole Nebula is that keyhole, looks like a peanut, a little bit, or a keyhole. Yeah, the homunculus, yeah. Need a bit more magnification though, I think, to make that out. But and there's also quite a few open clusters in that part of the nebula as well that we can make out too. So really nice image there by Dennis. And zooming in again, we've got this one here by Michael Barrow with a C-Star S50. Shorter exposures with the C-Star, 30 seconds, 215 of them, and this one's imaged over 4 nights. So Michael's collected the data from every night and then stacked and processed it in Cyril, which is the free software processing software that some of us are using at the moment. Greg Walton got this one with the 80mm refractor, which is actually the guide scope that sits on top of the Meade, or the spotting scope on top of the Meade. So that's a fairly wide field of view, and what Greg has actually done is starting to do a little bit of a mosaic. So he's got the 80mm image from the guide scope, or the spotting scope on the Meade, and he's taking images using the actual Meade and putting them together to create a mosaic. And I think this should start when I click it. So this is how all this is coming together. So a bit of a really nice project being done by Greg, and you can see just the amount of extra detail that you get out of the 14-inch Meade compared to the 80mm refractor is, yeah, it's pretty astounding. And that's another image of the keyhole taken by Greg, again on the Meade and a Canon camera. And this one here by Liam Laub, again this one's actually through the C11, I believe, out here in the dome. And what I'll point out in this photo, which you could see in previous ones as well, is this feature here, which I don't know, does anybody know what that is? Nope. Okay, this little thing here is called Mystic Mountain, and there was a famous Hubble image of Mystic Mountain that you may recognise. So that is the NASA version of it, and on the left is the crop from Liam's photo of the same object. So you can make out the same characteristics, the clouds coming across, the round structures up above it here. There's a couple of stars, which line up as well. But obviously a lot more detail from a space-based telescope than from our little C11 down here. So I thought that was a bit interesting. This one is by me, NGC 3532, the Pincushion Nebula. And I'll just show you where that sits in a minute, but there is a bit of, you can see the nebulosity around it. It's actually not too far from the Eta Carina Nebula itself. And if we go across, that's where that sits. So it's still sitting in the nebulosity of the Eta Carina complex there. That's why we're getting all that cloud and dust around it in the photo. And then we move over to the Gabriela Mistral Nebula, which was up in this part of Eta Carina. That's the Gabriela Mistral, and this is Gabriela Mistral and the Gem Cluster in the same field of view. Taken by Greg with the 14-inch Meade. So they're actually pretty close together. And the Gem Cluster is a really nice visual one to have a look at as well through the telescopes here. So a lot of the clusters around Carina that we're seeing, the nebula itself, and then a lot of the open clusters are really nice visual targets too, not just photographic. This is Nick's version of the Gabriela Mistral, taken with a 130mm refractor and his 294 ASI 294 camera, and he's used a couple of different filters. So what Nick has done is, using the two filters, the filters isolate hydrogen, oxygen and sodium emissions, and then what he does is he collects the data with the different filters, separates the channels, and then he recombines them in a different colour. So normally you get hydrogen is on the red, oxygen is around the green, blue, and sulphur is close to the red channel, I think, as well. But separating them out, Nick has recombined them: red as sulphur, H as hydrogen as green, and oxygen as blue. So RGB. So when you see this sort of wording here, SHO, that means red, green, blue, and it means sulphur is red, hydrogen is green, oxygen is blue, and that's what shows the different glow of different parts of the nebula through there. And also, this one might be a bit more obvious, but anybody recognise this? Down here, this part of the photo is the cosmic cliffs, also a James Webb photo. So on the right is the James Webb, on the left is Nick's photo of the same area, and that's just a crop from Nick's photo, and it's actually managed to get some really nice detail even in that really tight crop. There's some nice detail that Nick managed to get, although I think James Webb's marginally better. But yeah, some nice detail there as well, so that's pretty interesting too. I think it's great that from just with this hobby you get these space-based images and that sort of thing, and then you can relate them back to your own images and things, and you can identify them in your own photos, which is really interesting. Okay, another one by Nick. This one is NGC 3247, which is also called the Whirling Dervish Nebula. So this is around about a H2 region, H2 emissions, around about 13 to 14,000 light years away. And this is, again, similar process as the last one, where Nick has taken with the two different filters, or no, this one's just with the optolong, just with the dual band filter, so hydrogen and H and O, hang on. He does have the ASCAR filter there too, yes, you're right, sorry. ASCAR SO2 and the optolong filter, which is hydrogen and oxygen. And then he's recombined them in this colour palette, HOO, so hydrogen. The optolong is, yes, okay. I've confused myself here. So with, anyway, he's combined them in SO2 and HOO, and this is the SHO palette. Okay, that's what he's got there. So same colour palette as the Gabriela Mistral Nebula. And where this sits is right there, NGC 3247. It's just to the west of Eta Carina. So that's where that image, that's the area that image was taken in. And this is where the Statue of Liberty Nebula is, which is the next group of shots that we're about to see. So this series was taken by Greg with a 350mm Meade here and a Canon 60D. So there's a series of three shots. The first one is a single, just a single 30-second image. The next one is a stack of 20 images. So that shows you the brightness, the extra brightness that we get from stacking the images, and then he's adjusted the contrast and saturation to get the last image. So not a great deal of processing there, but with a bit of contrast and saturation, able to get a bit more detail out of the nebula there. And this is my Statue of Liberty. So this is a combination of some images I had taken a couple of years ago with the L-Extreme filter, which is again a hydrogen and oxygen filter. And last couple of weeks ago, I added around about 120 minutes with an Antilla tri-band filter, which is a red, green, blue filter. It's just a color filter. So I added that data to the previous one with the L-Extreme and came up with this version of it, just with an 80mm refractor. And the next one is Guido's, which is another really nice shot of Statue of Liberty with a 73mm zenith star. So that's a bit cropped, is it, Guido? That's not the. That's a bit of a crop of the full image, is it? Or
massive crop. Yeah.
Yeah, massive crop. But some really nice detail in there as well. So this is with the Optolong Extreme filter, again hydrogen and oxygen, processed in PixInsight, which is one of the better sort of software I think that's available for processing images. Then we've got the Southern Pleiades, Caldwell 102. Again, this is with my 80mm refractor, and this is processed by extracting the any nebulosity in the frame and discarding it, and then just processing the stars only. So that just gives it a bit of a clearer appearance. And we've actually got two clusters in this photo. So the Southern Pleiades is the bright stars that we see, and that's around about 530 light years away. The smaller cluster that you see down the bottom here is much further away. It's Malot 101, and it's about 6,500 light years away. So that's why, hence its faintness. And that's where the Southern Pleiades is. So you can actually see the Southern Pleiades by eye, and a lot of these other little clusters you can actually see by eye when it's dark enough as well. Okay, our next challenge is Earth and Sky. So we're looking at nightscapes, time lapses, sun and moon rises and sets. So tripod photos mostly, I suppose, with a camera and a tripod. But we're looking for images that have got both the sky and the ground in them. And fingers crossed, everyone, for a bit of an aurora maybe this month. I don't know. But yeah, get out there with a tripod and see if we can get some nice nightscape photos for the next challenge. So when you get your photos, send them in to me, either send them to Facebook or eScorpius, or email them directly to me, and I'll include them in the challenge. Also, just make sure you post a bit of information with your photo as well, of what you're actually photographing, how you photographed it, and that sort of thing. When you photographed it, just helps me talk about it a little bit better. And our contributors board has got quite a few more names on it this month. So if you want to get your name on this board, start taking photos and sending them in. Okay, that was AstroMofo for this month. Any questions, anyone? Yes?
Do you know anything about the Dwarf 3? Is it any...
No, I don't know anything about it. I don't know anyone that's got one. We do have sea stars here, and we do also have a camera scope called Vespera, which we'll be using soon. So it's a similar sort of thing. Works pretty much the same way as the sea star, but I wouldn't be able to tell you which is better or which is worse. Yeah. Just on that as well, we do have, like, we've got our sea star and we've got our Vespera, and if anyone is interested in driving those scopes on a PVN, come and see me, because we do need people to be actually able to drive them, point them at objects, learn how to use them, and just to be able to show people at the PVNs. The other news is, before I go, is we've got a new computer that we're going to be bringing down here soon, which has got a little bit of extra processing power and a video card in it, so we can actually start doing some tutorials and some workshops on image processing and that sort of thing. So I'll bring that down to the working bee on Saturday, and if anyone's interested in having a look at some of the software that we're using, you're more than welcome to come and ask some questions or have a look.
All right, so this is Sky for the month for the rest of April and then the first half of May. We've already seen plenty of nice photos before. I think this MoFo challenge was must have been one of the biggest ones we've had so far, right? Yeah. The Aurora one was pretty big too, but yeah. Anyway, I still put an image of that Nick took, and this is the current image in the Morning Peninsula magazine article of the Southern Tadpole Nebula. So another really, really great one. All right, so Sky for the month. So we're looking at 16th of April to mid-May or so. So this is the current view of our solar system. So we can see, let me try and use the pointer here. You can see Earth around here at the moment. This is the view from the top. And so everything to this side of Earth is in the morning sky. Everything to this side of Earth is in the evening sky or night sky. And then obviously everything directly behind the sun is during the day, so not visible to us. So as we can see here, Mercury is currently in the morning sky, and well, Venus isn't shown here, but this is Venus. This is the orbit of Venus, so that's also in the morning sky. We'll see that in a bit when I start the animation, I think. Hang on, this is going the wrong way, isn't it? I will have to check that. We may be looking at this from from below this this time. I didn't notice that when I put it together. we're not moving back in time, so so just to change things up this month, we're looking up at the sun rather than down from above. Okay. So when we zoom out a bit to the outer solar system, we can see where the outer planets are, and yeah, as you can see, Saturn and Neptune in a similar part of the sky, and Jupiter and Uranus in a similar part of the sky as well. And we'll see that in the all-sky view in a minute, where they actually are and whether we can see any of them or when. So let's have a look at the all-sky view. This is the 1st of May now from around here, so looking south, and we're starting at around 5:30 p.m. And the sun will set pretty soon after that. But we can see that on the 1st of May we will have Jupiter, Mars, and the Moon relatively close to the sun already at sunset. So sunset around 5:30 p.m. And because we've got the Moon on that slide here, the new Moon will be on the 28th of April, so just a couple of days before this view here. So you can see the Moon has basically just reappeared from being lost in the glare of the sun. And then the next full moon will be on the 13th of May, and the new moon again in May on the 27th. Yeah, as we can see, Jupiter is now setting in the early evening, around 7:30 p.m., so around 2 hours after sunset. Mars will be setting around 11 p.m., and Uranus will be in conjunction with the sun on the 18th of May, so also not visible. If we just fast forward a little bit, well, we can see Jupiter setting there, yeah, around 7:30. So Mars will still be in the sky for another couple of hours or so. But then we've basically lost the planets for at least the next few months. So this is now around 10 p.m. at night on the 1st of May. And we can see that if we look at the major, like the brightest stars in the sky, we now have Sirius and Canopus already relatively close to the horizon at that time. And we have the stars of the Southern Cross and the two pointers really high up in the sky around 10 p.m. And then in the east we have Antares and Arcturus. So Antares, of course, is part of the Scorpion. So if we just change this view to have the constellations, that's a bit faint to see really, but we've got Scorpius here, the Scorpion, and then Sagittarius below it. That definitely tells us that we're getting closer to winter now, and as we can see, the Southern Cross really high up in the sky around 10 p.m. And yeah, when we look at this, the constellations that we just went through for Astromorpho, right, we have Carina, Vela, and Puppis also still very high in the sky. So if you want to get a chance to look at some of those objects that we just saw, now is a really good time. Right? They're nice and high and very, very good to view. Now, this is 10 p.m. If we fast forward a little bit more, we can see Scorpius around here. So that's now becoming really prominent at night. So after midnight, it'll be getting closer to the zenith now, and also the core of the Milky Way now between midnight and 2 a.m. or so, very available. And then we can see towards the morning, all of the other planets are coming out. So we have Saturn, Venus, Neptune, and Mercury up there. So Venus is a very bright object before dawn, rising around 3:45. Saturn actually rises a little bit earlier than that, 3:30. It's now actually possible to see it with the rings basically edge on, as we can see them at the moment. If you get up around 5 a.m. or so, you still get a good chance to view Saturn before sunrise. And Mercury will be observable just before dawn, but it's relatively close to the sun. So if we go a little bit further, you can see sunrise is around 7 a.m. now in May. And I think that's pretty much what we had for the overview here. Just a quick look at the relative apparent sizes of the planets. Venus still appearing very large at the moment. Jupiter and Saturn getting smaller as we're getting away from them. And so is Mars. So probably for the next few months, we'll focus on nebulas and galaxies rather than planets. No comets brighter than magnitude 10 for the next month. So I think we will basically repeat this slide for the next 3 or 4 months or so. There's nothing on the horizon. But we have meteor showers. So the Eta Aquarids are happening from the 29th of April, peaking in the early morning on the 6th of May. And this could be a good one. So according to the information from the astronomy yearbook or from the almanac, we have a maximum rate of about 40 per hour. I'm not sure if this is true for our location here. That might be the peak at the best possible location to observe. But they are remnants of Halley's Comet. So we're basically, the Earth is now moving through that part of the sky where Halley's Comet left a lot of debris. And that causes this really nice meteor shower. And on the morning of the 6th of May, the moon will actually set around midnight. So meteor showers are usually best viewed around the early morning because we're basically traveling in that direction. So the moon shouldn't be interfering with this one. So it might be a good opportunity. The other 2 meteor showers that are mentioned in the almanac are the Lyrids and the Pi Pupids, but they are both affected by the moon this year, and probably not as spectacular anyway in the first place. But also both peaking around between the 22nd and 24th of April. And I think that's all for tonight. So the sources, as always, Stellarium, the NASA website, Eyes on the Solar System, and the 2025 Astronomy Yearbook. Any questions?
All right, so this series of 3 shorter talks about astronomical spectroscopy will go in total for about an hour. So if any of you are interested in a cup of tea or coffee, feel free to get up and quietly go out and have something anytime and come on back in. So the first is going to be given by Professor Martin McCoustra of Herriot-Watt University in the UK. The second by Professor Serena Viti, shown standing there on the right-hand side, from Leiden Observatory in the Netherlands. And the last, physical chemist, Professor Wendy Brown from the University of Sussex. Now this is from 2023 and it's courtesy of the Royal Society of Chemistry.
I'm Natalie Starkey from Chemistry World, and I'm here with you for the next hour, where I'll be joined by 3 guests working at the forefront of astrochemistry research. Now, it might seem to the untrained eye that the vastness of space is mostly empty, but in recent years, powerful new telescopes, including ALMA, the Atacama Large Millimeter Array, and the James Webb Space Telescope, JWST, which launched in 2021, have further revealed the complex chemistry of the gaps between stars and planets, showing that these extreme and often very cold environments are home to abundant amounts of complex chemistry. Now, the 3 scientists joining us today are not just going to tell us how they're discovering more about the chemistry of space, but they're also here to answer any burning questions you have about the topic. So I'd like to invite all our speakers on screen now. We've got Martin, Serena and Wendy. We've got all of them appearing. I'll just give a short introduction about each of them and then we'll move on to hearing from them because you don't want to hear from me, you'll come to hear from our amazing astrochemists. So Martin is a graduate of Herriot-Watt University. He moved to the University of Nottingham in 1994 and rose through the ranks to hold a personal chair in chemical physics before returning to Herriot-Watt. Martin's research interests focus on physical and chemical processes on complex surfaces, in particular the physics and chemistry of the astronomical gas-green interaction and plasma modification and erosion of polymers and plastics. After Martin, we'll hear from Serena Viti, who is Professor of Molecular Astrophysics at Leiden Observatory. Serena has served as the head of the Astrophysics Group at UCL from 2016. Her research interests span a wide range of topics, centred around the role of molecules in space, especially in the dense gas of the interstellar medium and star-forming regions. Her most recent work concentrates on the interpretation of molecular observations in nearby galaxies and on devising novel techniques for astrochemistry involving machine learning. So lots of stuff to cover there. I'm very excited to hear from both of them. We also have Wendy Brown, who is Professor of Physical Chemistry and Head of the Department of Chemistry at the University of Sussex. She's a surface chemist using techniques to study model astrophysical ices. She collaborates with physicists and astronomers to undertake work that can be used to model astrophysical processes and to help interpret observational data. So as you can probably tell from these introductions, we've got a really wide range of expertise here, and the speakers are going to link up all of the work together to really give you a great overview of this topic. I'm going to hand over to Martin first, who's got some slides to share, and then we'll hear from him, and then we'll have Serena and Wendy after that. Okay, so let's get Martin's presentation on screen.
Okay. I'm going to paraphrase a statement by a very famous British author called Douglas Adams, and that is that space is big, very, very big. And to add something to that, it's a long way away. And we really can't go out there and physically measure stuff as we do in chemistry laboratories here on Earth. The other problem is there's lots of different environments out there. And how do we know that? Well, it's spectroscopy that really gives us that handle. The various environments are very intimately tied up with the process of forming stars. And the animation that's now on the screen is a nice animation that came from it was originally developed for the Hubble telescope, but it comes from the James Webb Space Telescope website. And really the key issue in a large area of astrophysics is understanding how the universe evolves, particularly perhaps our local galaxy and other galaxies, how we go from the diffuse medium into the dense medium as the animation is now taking us, how gravity pulls together the gas to warm up clumps of gas, how angular momentum starts those clumps of gas to spin, and eventually we get a star forming in the center of the gas clump, ejecting material back into space through the jets. The gas itself starts to form a set of planetary rings, and the planets themselves condense. So we've got a process that takes billions of years. So the chemistry we're looking at is occurring over those time scales as well. Once you get your star, then your star will live, depending on its size, for a few billion years. Our own sun, for example, is middle-aged, and we'll go through this process shown on the screen here, from being a sunlight star to a red giant. And as it gets bigger and older, it starts to eject matter back into interstellar medium. With larger stars, the process is much shorter and much more violent. But again, the goal is that the outcome is that material is ejected from the star as it dies back into space, enriching the environment, enriching the periodic table that we have to play with when it comes to astrochemistry. Now, it's surprising to think that spectroscopic observations of sunlight and starlight actually started in the mid-1600s, but then we know when telescopes were invented, 100 or so years before that. But it took until the mid-19th century that we could have spectra of the quality shown in this slide, where we could identify absorption features in the atmosphere of our own sun. And this is the work of Fraunhofer, who then, with Bunsen and others, helped identify the elemental composition of the species absorbing that light from our star. After 100 or so years of observations of stars in space, astronomers were convinced that basically space was too harsh and molecules too fragile to exist. But a big surprise came along in the 1930s. Well, really, there were two surprises. First was the observation of what are known as diffuse interstellar bands. Rather than being nice and narrow like atomic lines, these were very broad. And for the most part, these are still not assigned to any particular species. There are one or two that are, and have been identified as, for example, fullerene ions. But the real molecular astronomy begins with the observations of small diatomic species in the optical spectra of nearby stars. From that time in the 1930s, we've seen a variety of new observational platforms come along, new ways to look out into space, radio astronomy, infrared astronomy, millimeter wave astronomy. These have all opened new windows on space and allowed the number of observed molecules to grow now to somewhere of the order of 250 or so. And it appears to be kicking up exponentially in recent years. Most of those molecules, I will say, are in the gas phase, but there are very clear identifications of some solid state materials, water ice, carbon monoxide ice, carbon dioxide ice, and others. So we've now got a fairly rich chemistry, simple radicals and ions on top of all the atoms we know about, simple molecules, closed shell systems, and there are also what the astronomers call complex molecules. Of course, for many chemists, something like ethanol or acetic acid is not particularly complex, but it is in interstellar space. There are even hints, some disputed, as to observations on glycine and other amino acids and prebiotics. Molecules are found in many of those regions that I mentioned on the first slide, but the most complex are generally observed in dense regions where stars and planets are forming. And that points to some very crucial roles for molecules in space. The cosmos really is, today, chemically controlled. The first one is the obvious one, and this is what Serena Viti will be talking about when I finish. It tells us about remote environments. It tells us their temperatures, their densities, and the movement of the gas within those environments. Molecules are also crucial for maintaining the rate of star formation. And surprisingly there, the key point is that it's molecules in the solid state that matter. Now, the collapse of a gas clump is generally prevented by the presence of a magnetic field due to the ions moving around within the gas. We've recently discovered that carbon monoxide ice and water ice formed from dipolar molecules don't order in the solid state in the way that we might expect, as shown on the left-hand side of this graphic. That is the minimum energy structure that we would expect. Dipoles are all counter-aligned, the charges cancelling out. Experimentally, we find the opposite is true. We find that through an entropy-driven process, the ice is polarized. And because of that polarization, they can help to remove ions and other charged particles from the gas phase, switching off the magnetic support, the magnetic field that prevents collapse to form the star. Molecules are also crucial for making small stars, because another factor that prevents star formation is thermal motion in the gas. The faster the atoms and molecules move, the less likely gravity is going to help to collapse them. But if the molecules emit radiation, and that's the radiation that we eventually can detect, it removes the bottleneck. And it allows us to make small stars like the sun. Small stars have the advantage that they live a long time. Which brings us on to the final aspect for chemistry in the universe. Chemistry seeds the universe with the potential for life. The icy dust grains that Wendy Brown is going to talk about are nanofactories, where simple molecules are cooked up through the influence of starlight and stellar winds to produce complex chemical soup. Complex enough to kickstart biochemistry. How do we know that? Well, it's delivered to Earth. Well, it was delivered to Earth 4.5 billion years ago when the Earth formed through the comets. We can tell that because we have data from observations by the Rosetta mission on the gas surrounding the comet 67P. We have data from meteorites, carbon-rich meteorites that have landed on Earth, like the Murchison meteorite. And those tell us, the latter in particular, that all of the building blocks in terrestrial biochemistry were present on those meteorites. And more importantly, they had the correct chirality. A chirality consistent with the biochemistry, the chirality expressed by terrestrial biochemistry. There's lots of ways we can do chemistry out there. I'm not going to go through detailing about this. It's a really nice little article that myself, Dave Williams, and Helen Fraser wrote many years ago. But there's a mix of gas phase chemistry and solid state chemistry and surface chemistry. Those chemical processes are fundamentally driven by the energy obtained from light and cosmic ray interactions. At that point, I'll draw to a close and hand over to our second speaker, Professor Serena Viti from the University of Leiden. Serena.
Excellent. Thank you very much, Natalie. And thank you very much, Martin, for a great introduction. And I hope to be able to continue from where Martin stopped. And in particular, I'm going to show you the more observational aspect of astronomical spectroscopy. And indeed, we shall, first of all, zooming a little bit more into how we actually can observe atoms and molecules in space. Martin has already given you an overview of what spectroscopy is, but let me indeed reiterate how we can observe molecules, but also in particular, why do we need to observe molecules in the first place? And as Martin hinted to you already, it's because molecules for us are like tools. They're tools to understand and characterize the physical characteristics and the chemistry of the clouds, which are our stellar nurseries, so the clouds where stars and eventually planets will form. So our knowledge of how stars and planets form comes from many aspects, but for a start, we need to understand the gas, the very cold gas that from where everything starts. And the way we do that is by observing the radiation, many different types of radiation that is either emitted or absorbed by the atoms, but in particular by the molecules, as Martin has already explained. So the way the molecules can react with light is either by absorbing it, if there is a background source, or let's say a background star, like here in this little cartoon, for example. And this is how then the spectrum will be affected by these absorption lines. Or alternatively, our molecules can also spontaneously emit the radiation, and then what will happen is that you will have emission line in your spectrum. No matter in what form the molecules tell us this information, what is important here is that that can only happen in the forms of spectral lines over certain wavelengths. And unfortunately, these wavelengths are not in the optical, so then we cannot really see it with our own eyes, because the clouds from where the molecules are emitting are actually very opaque to both visible light and to ultraviolet wavelengths. And so the observational regime that we observe molecules in is in either the infrared or in the submillimeter wavelengths. And this is what we will be talking about in the next few minutes or so. Let me first introduce you to the wonderful instruments that allow us to observe molecules in space. I shall start from, and this is not comprehensive by any means, it's just all the telescopes that could fit in one slide. But let me start from those which are on the ground. So these are the telescopes that observed in the millimeter wavelengths. And you will see from these pictures that we have some which are a collection of dishes, and some which is instead just as one large dish, like IRAM or the JCMT or APEX, for example. So what's the difference between these different configurations? So the difference is that a big dish, such as this one, for example, can collect a lot of light from a very large field of view. But the resolution, what we call the spatial resolution, so that means the details with which we can see space, it's not so good compared to what a configuration such as ALMA that Natalie already mentioned during her introduction can give us. So this is called an interferometer, and it's essentially a collection of dishes, and they're all collecting the light from the same place. And then through various quite complex techniques, we managed to combine the light from all these different dishes, and then we interpret the light as coming from molecules. All these telescopes are in wonderful places, in Chile, in Hawaii, for example, or on the Alps. And that's because it allows us to observe in fairly pristine conditions where there is little light pollution and very dry weather. But of course, we can also observe from space, and in principle, that's better, of course, because we are above the atmosphere. And in that case, we can observe in wavelength regimes like infrared, which are almost impossible to observe from the Earth. And as you've already heard, of course, we now have the JWST, the James Webb Space Telescope up there, collecting wonderful observations for us. But there were some predecessors to the JWST. In particular, we start from ISO, the Infrared Space Observatory, Spitzer, and Herschel. All wonderful telescopes that gave us a lot of data that we are in fact still analyzing. What is it that we obtain with these telescopes? Let's look at some spectra to give you a feeling of how busy we are analyzing data. This, for example, is a sample of a spectrum, which we call a line survey, because we essentially, what we do, we point a telescope, in this case, the Herschel Space Telescope, to a region, in this case is Sagittarius B2, which is a massive star-forming region towards the center of our galaxy. And we scan a certain wavelength region, in this case, going from 100 to 600 micrometer. And as you can see from the spectra, there are lots of lines there. And the key point that I want to make is that these lines are all molecular lines. Nothing is noise. So if you zoom in into any of these little sequences, you will find thousands of lines, which all need to be identified and interpreted. And each of this molecule, each of this molecular line, can give us valuable information about the physics and about the conditions of the star-forming clouds, in particular, the density, the temperature, and so on. The next slide that I'm going to show you is, again, another spectrum, but I'll tell you why this is almost even more exciting than the spectrum that I'm showing you now. This is, as you can see, very, very busy. Many, many, many lines, all being identified. And what is, to me, astonishing about the spectrum is that this is a spectrum from a cloud, or from many clouds, not in our own galaxy, but in another galaxy far away. This is a galaxy which is called the starburst galaxy. Starburst meaning that it's a galaxy which is very, very rich in stars. And in particular, there are bursts of stars forming all the time. And as a consequence, the gas is very rich. And our telescopes now are so sensitive that we are able to observe many, many molecules in star-forming clouds in other galaxies. So, all this complexity, how come? How can we have such complexity in space? Martin has already mentioned how harsh the conditions in space are. We are talking about really, really low pressures compared to the pressures in our own atmospheres. Many, many orders of magnitudes lower. And temperature-wise, we're talking about temperatures of minus 260 degrees Celsius. So it's really, really was very surprising at the beginning that chemistry or molecular chemistry could happen at all. In fact, the way it happens is that something must drive it. There are many drivers that are available in the interstellar medium. And in particular, there's starlight, of course. There are loads of photons coming from stars. There are cosmic rays. There is dust, which will be the topic of Wendy Brown. And of course, there are many violent events that can lead to shocks. And all this can drive the chemistry. And so what I'm going to do in the last couple of minutes is really just give you a little tour about examples of a bit more details maybe about what type of molecules we can observe depending on the drivers available in the interstellar medium. So this is a busy slide. Let me go through it quickly. So I wanted to give you an example of what type of chemistry is driven by cosmic rays. Cosmic rays are very important in the early stages of star formation when the cloud is dense but really, really cold. And so the chemistry there is kick-started by cosmic rays. And what you're seeing here on the right-hand side is a map in depth, really, of a particular cloud, a very famous cloud called the Taurus molecular cloud. And here you just see essentially a different depths within the cloud. And on the left-hand side are our spectra. So these are various molecules that we observed there: carbon monoxide, HCO+, CS, and you see the spectra of these various molecules in different places in the clouds. And really my message here is just look how different this wiggly line, the spectra, are from each other. And there are these differences that allow us, through various tools and various modeling tools to decipher the densities, the temperatures, and the various conditions in these very cold, dark clouds. Equally, when the stars are forming, we can witness their formation by looking at more complex molecules. This complexity happens on the dust, and I shall leave it there and won't say anything more because Wendy will tell you all about it. But suffices to say that it's the dust that allow us essentially to allow complex molecules, what we astronomers call complex, to form in space, and we then observe these molecules during the formation of the star. And finally, as the stars are being born, they always go hand in hand with violent events that we call jets and outflows, which you can see here in the infrared. And as you can see here in the visible, is just a dark patch. But in the infrared, you can see already that it's a powerful jet. And when we observe molecules which are produced by these jets, we can decipher and determine the characteristics of the jets. In this case, what shocks and what these violent events do, they allow high temperature chemistry to actually occur in space because they give energy to the gas, and so a different chemistry from the cold chemistry will occur. And of course, so far I've just mentioned about observations of molecules in the gas, but you can also observe molecules which are in the solid state on the dust.
And we'll try and get Serena back. I think she was probably on her last slide, just about.
Hi everybody, so my name is Wendy Brown. I'm from the University of Sussex, and I'm going to tell you a little bit about the things that we can learn by doing astrochemistry in the laboratory. And in particular, I'm going to tell you how the laboratory experiments can help us to identify some of the type of spectra that Serena has showed us from observational astronomy, and the types of things that we can learn when we do experiments in the lab. So I'm going to focus on the interstellar medium. The interstellar medium is the space in between the stars. So most of us would think that the space in between the stars is completely empty, but pictures like this beautiful picture here from the James Webb Space Telescope of the Carina Nebula show us that in fact the interstellar medium is definitely not empty. We have large clouds of gas and also dust found in star-forming regions. And these regions are nurseries for new stars, but from a chemist's point of view, the interesting thing is that they're rich in molecules. And Serena and also Martin have mentioned that dust could actually play a very important role in the formation of molecules. And it's on chemistry that takes place on dust grains that I'm going to focus when I talk about laboratory astrochemistry. So what do we know about dust grains in interstellar medium? They're mainly made of carbon-based materials and silicon-based materials. And at the temperatures of the interstellar medium that Serena already mentioned, maybe -240 to -260 degrees centigrade, they're covered in ice. Now, when I say ice, most of us would think about water as being the main component of ice, and that's absolutely true in interstellar space. The largest component of molecular ices in space is water. However, there are some other very, very important species. Martin mentioned that we have solid carbon monoxide, which is frozen out in ice. We also have solid methanol, and we have things like ammonia and methane. But very importantly, we also have organic molecules. And organic molecules are, of course, very much of interest because those are the types of things that can lead to biomolecules that might have seeded the Earth. So I'm a surface chemist, so I'm interested in processes which take place on surfaces. So let's think about what happens to this ice-covered dust grain in space. It doesn't just sit there with nothing happening. In fact, it's processed. And it's processed in a whole range of different ways. So if we start with gas phase bombardment, in space, the most abundant species is actually the hydrogen atom. And so our ice-covered dust grain is going to be bombarded by atoms all of the time. And I mean all of the time on a space-time scale, of course, not on our time scale, because things take much longer in space than they do on Earth. But what happens, for example, when hydrogen atoms bombard the carbon monoxide, for example, that's found in our ice, is that we get hydrogen additions to the carbon monoxide, which can then go on to make methanol. And laboratory experiments have shown that this is actually the way that we make methanol in space. It's made on a grain surface, and hydrogenation of carbon monoxide leads to the formation of the methanol molecule. Now, of course, Serena and Martin have already mentioned that we've got lots of light around in space, and light, of course, in particular ultraviolet light, will make chemistry happen. And so if we think about our own sun, it's a big source of ultraviolet radiation. Ultraviolet radiation has an effect where it can dissociate our molecules. So if we take our methanol molecule, if it's irradiated with ultraviolet light, it can split into individual components. Now, these components are not very happy because they are no longer bonded to make a stable molecule. So in fact, they become radicals, which are very reactive. And this is one way in which some of the organic molecules that we find in space can be formed by reactions of these types of radicals from photodissociation. But irradiation with ultraviolet radiation, for example, can also lead to these molecules coming off of the grain surface, so-called photodesorption. And so in that case, now we've got a way for taking our species from the grain surface and putting them back into the gas phase. The final type of processing that's important is thermal processing. And thermal processing basically happens as the star ages. At the beginning of the star's life, it's very cold, but as it ages, it warms up. And we all know what happens on a cold morning when we've got ice on the windscreen of our car. As it gets a bit warmer, that ice starts to melt and comes off of the surface of the windscreen. And it's just the same process. As the star ages and the grains warm up, the species that we find in the ice end up back in the gas phase. And so once they're back in the gas phase, of course, they're then available for reactions to take place in the gas phase as well. Now, as surface chemists, my group are interested in studying all of these different types of reactions. And people who look at surface reactions of relevance to astrochemistry study all of these different processes. I'm not going to tell you about all of these today because there isn't time, but I'm going to give you a flavour of some of the things we can find out in the laboratory. Now, if we're going to do laboratory experiments, we've obviously got to try and recreate the harsh conditions of space in the lab. Serena already mentioned that we have very low temperatures, about -240 to -260 degrees centigrade. So if we're going to do an experiment in the lab, we're going to need to cool our model dust grain surface down to those types of temperatures. And we do this using a closed cycle helium refrigerator. You can just see the top of the refrigerator here, and it's basically connected to our sample, which is in the middle of the chamber here, and it's cooling it down to about -250 degrees centigrade. Serena also mentioned the very low pressures in space. The pressure in space is about 10 to the -21 atmospheres. That's 10 million times lower than atmospheric pressure. Now, actually, it's pretty difficult to recreate exactly that low pressure in space, but we can create what we call ultra high vacuum, and that's what this metal vacuum chamber is designed to do. It allows us to get to very low pressures to simulate the low pressure conditions in space. In the experiments we do in my laboratory, we look at graphitic model dust grain surfaces, so carbon-based dust grain surfaces. Other researchers look at silicon-based grain surfaces and also mineral types of grain surfaces. But in our case, we look at graphitic dust grain surfaces, and we grow interstellar ices in situ in the vacuum chamber, and then we analyze them using various techniques. So what types of techniques can we use to analyze molecules on surfaces? Well, the first one is surface infrared spectroscopy. So here's our molecule bonded to the surface. We send infrared light in. That infrared light, some of it is absorbed by the molecule. That excites vibrations within the molecule, and then the light that is not absorbed is reflected off of the surface. And if we look at the difference between the incident and the reflected light, it tells us about the vibrations that have been excited. And what's really fantastic about infrared spectroscopy is that it acts as a fingerprinting technique for molecules. And this is, of course, one of the ways in which the infrared telescopes that Serena has told us about allow us to identify the molecules that we've seen. We also use a mass spectrometry technique known as temperature programmed desorption. So here are our molecules. They're stuck onto our surface. What we do is we heat the surface. You can see in the top right-hand side here, the temperature is increasing. As the temperature increases, molecules come off of the surface at different temperatures and go into our mass spectrometer. On the bottom right-hand of this slide, you can see the mass spectrometer signal as a function of temperature. And what we can see is that different things come off at different temperatures. And of course, the thing that we know is that something that's more strongly bound to the surface will come off at a higher temperature. And so spectroscopy like this will allow us to determine the binding energy of the species to the surface. So how well can we do? Well, this is a spectrum that was recorded of icy covered grains by the Infrared Space Observatory that Serena mentioned. This has been around for a number of years now, but very importantly, we can see the grains themselves, the silicate grains, and we can see some of the components of the ice: carbon dioxide, carbonyl sulfide, water, of course, I mentioned, methanol, etc. Now, in the laboratory, we can basically do as well as we want to. We could make an ice containing all of these different species, but of course, if we did that, the physical chemistry would be quite hard to interpret. So we tend to go for ices with slightly less components. And here you can see an example of a laboratory ice that we've grown. We've got water, carbon dioxide, methanol, and in this case, carbonyl sulfide. But we can basically do as well as we like, and we can investigate the types of ices that we want to be able to study and that we see in space. So what type of data can we obtain? And I'm not going to be able to give you an exhaustive list of all of the data. I'm only going to be able to give you a little flavour. But one thing that we can do is record infrared spectroscopy in the laboratory that can help to identify the myriads of lines that we can see in the type of spectra that Serena showed you. So, for example, in an observational spectrum, we might see a line that we assign to a particular molecule, but we want to know whether that molecule is in an environment where there's lots of water or is in an environment where there's lots of methanol. And so what we can do is we can record spectra like that for different molecules in the lab, and then we can compare them to the spectra we record observationally. And here I've just got an example for a family of isomers, the C2O2H4 isomers. All of these have been detected in space. The three isomers are acetic acid, methylformate, and glycolaldehyde. And you can see that the infrared spectra, in this case, in the presence of water ice, are very different for these. So it shows us how we will be able to identify these. We can also use our mass spectrometry technique, the temperature programmed desorption, to determine binding energies. And here I've got an example for one of those isomers, in this case, methylformate. These are the types of data that we record. In this particular case, they don't look all that exciting, but what they really do give us, which is extremely useful, is the strength of binding of this molecule to the surface. And it turns out that these binding energies are absolutely crucial for astrophysical modelers because they need to put these into the models of things like, for example, the star formation process. And it's only in the laboratory that we can actually measure these types of numbers. We can also use temperature programmed desorption to explore trapping. Now, in order to explain what I mean by trapping, I need to talk a little bit about water ice. So on the left-hand side here, we have a temperature programmed desorption spectrum for water ice. And the bit that matters here is this bump on the low temperature side. And it turns out that this bump is actually really, really important because this bump actually tells us about a phase change that takes place in the water ice. So if you look at the cartoon on the right-hand side, when we grow water ice on a surface at very low temperatures, which is what we would have in space, it's very porous and amorphous, and it looks like a sponge. So the blue here shows us what the water looks like. That means if I have another molecule that I stick on top of that, in this case shown by the red, that molecule is going to fall into these holes. And if we heat the surface up then, and the water ice changes shape, the first thing that happens is that these porous areas of the surface close up and the molecules get trapped within the surface. If we then heat a bit further, our water crystallizes, and that's signified by this bump in the temperature programmed desorption spectrum. And as this crystallization takes place, this allows the molecules that were trapped to be ejected. And it turns out then that water ice has a really important role to play in telling us how various molecules might behave in space. So I'll give you an example again, using methyl formate as my example. On the left-hand side, I've got temperature programmed desorption spectrum for methyl formate in different ice configurations. I've got the water TPD spectrum for comparison at the top. So the bottom temperature programmed desorption corresponds to our methyl formate adsorbed directly onto a model grain surface. That isn't really what we were expecting to see in space. In space, there's lots of water around. So the next spectrum actually shows our molecule, which is stuck on top of water ice, which has grown on our graphite surface. And you can immediately see that the spectra are completely different. The water is affecting the behavior of the methyl formate. We can also dose our methyl formate in a mixture with water ice. And of course, this is much more likely to be like the type of thing we're going to see in space. And again, you can see that the spectrum is different. And if we look carefully, we can actually see that when we've got this bump on our water temperature programmed desorption spectrum, we've got a large amount of the methyl formate coming off of the surface when the molecule phase transition takes place. We can also see that some of the methyl formate comes off with the bulk of the water ice. But the most important thing to notice here is that these spectra in the presence of water ice are very different to those for the pure molecule. So the temperature programmed desorption can tell us about how the molecule traps. And this is also really important for things like models of star formation and planet formation. Okay, so let me just finish by summarizing what I've told you about laboratory experiments. Surface and ice chemistry are extremely important in space, and it's thought to be the way that a number of different molecules are formed. We can recreate the harsh conditions of space, the low pressure and low temperature, and that allows us to do laboratory investigations which can help with assignment of observational spectra, amongst other things. Mass spectrometry in the form of temperature programmed desorption can help us to determine things like desorption kinetics and also trapping in ices, and both of these are extremely important for models, and both Martin McCoustra and myself have given data to Serena to put into astrophysical models. And as I showed you, water has a very big effect on other species. Now I'm going to finish with a slide that basically summarizes the whole of this webinar. So I hope between us that myself and Serena and Martin have shown you that astrochemistry is an interdisciplinary subject area that can tell us a lot about the chemistry that occurs in space. We've seen from all of the talks that molecules are found in many different regions of space, and these molecules are formed in both the gas phase and on grain surfaces, and I tried to tell you a little bit about that during my talk. We use spectroscopy to identify molecules in space. Without spectroscopy, we would be completely stuck. And the James Webb Space Telescope has opened up a whole new area of observational spectroscopy, and we're hoping very soon to be able to see some organic molecules with the James Webb Space Telescope in ice. And finally, laboratory data can help us to interpret the observations and provide input for astrophysical models. And with that, I'm going to finish this part of the webinar and hand back over to Natalie.
Excellent, thank you so much. I'll invite Serena and Martin back on screen now, because we're going to enter into the Q&A section of the webinar with our audience. We've had millions of questions in, so I'm going to try and get through a lot. I thought, Wendy, I was just looking at that setup of your lab, and I'm just amazed that it's even possible to recreate, these conditions that we have in space within a lab. How long does it take you to build that lab, and how many people work in there?
That's a good question. If you talk about building it from zero, so when we have an empty lab, then it can take 6 to 12 months to build that type of vacuum chamber. But if you talk about on a day-to-day basis, the vacuum chamber sits there in our lab, and it probably takes us around about an hour to get ready to do an experiment. Our sample stays at about -250 degrees centigrade all of the time, and our sample is in there and it's cold. And when we're ready to do an experiment, we basically clean the sample just by heating it, and then we're ready to dose basically whatever we want to study. So if we want to study an ice that contains water and methanol, we can dose our water and methanol into the chamber. If we want to study one that contains water, CO2, CO, methanol, we can dose all of these. And that's actually a relatively fast process. In my lab at the moment, I have 2 PhD students plus a final year undergraduate MChem student. So one piece of apparatus usually has 2 people on it. So yeah.
Brilliant. That's amazing. I just think it's so cool that you can build these instruments that can, you know, real analogues for space. It's absolutely fascinating. We've actually had a question related to, you know, how would we get into working in fields like this? So obviously astrochemistry, probably lots of people when they're studying at school don't even know this is something that they can do. Where do your PhD students come from? What kind of backgrounds are they coming from in terms of their education? And that's open to
actually a range of backgrounds. So my 2 PhD students at the moment are both chemists by training, but I've also had people who've done physics degrees come to work for me. I've also had people who previously have not worked in the laboratory, who but had a background, for example, a master's in astrophysical modeling or astrochemistry, who then came and worked in the laboratory. But it's usually someone with either a chemistry background or a physics background. An engineering background is okay too. I believe Martin has had students with engineering backgrounds in the past. It's slightly different, of course, for Serena, because Serena doesn't work in the lab. She does observational and modeling work. But in terms of the lab, mostly chemistry and physics, but occasionally engineering students would be.
Yeah, so Serena, does that differ much for you? Is it more physicists that you're working with?
No, I think we have a very large cross-section with those who would also go to the lab, in the sense that if you have a degree in astrophysics or in physics, you certainly be suitable for a PhD in astrochemistry. I have to say I've also had students with backgrounds in computer science, actually, because of a lot of the type of modeling that we do. It's also sometimes involving machine learning and statistical techniques. So physics, chemistry, computer science are all excellent backgrounds.
Excellent. And Martin, yeah, I'm just going to ask how did you all get into this? I know that a lot of space scientists or people working in space come in, as we've said, from lots of different angles. And I guess that's part of the joy of the field, that we've got all these different minds coming from different backgrounds, working on the same problem, but just coming at it from different angles. That diversity of thought is really important, isn't it? Martin, I don't know if you've got anything to add on that.
I started out doing spectroscopy and photochemistry in the gas phase. And my PhD is looking at the photodissociation of small molecules in the gas phase. But when I was looking for an academic position, I decided to move into looking at processes at the gas-solid interface, initially related to catalysis on single crystals, but then through interactions with a colleague in atmospheric chemistry, I got involved in looking at the role of water ice in ozone depletion in the late 1980s, early 1990s, when the ozone hole was discovered over Antarctica. And just before moving from my first appointment at UEA to Nottingham, I read an article by David Williams in the predecessor of Chemistry World, Chemistry in Britain. And that article really inspired me. I went to meet David and talk to him, and Wendy and Serena know the rest of the story.
That's amazing. Thank you for sharing that. I do want to move on to some science. We've had lots and lots of questions about very specific questions as well, and I'm going to try and maybe summarize some of the questions or combine them. So sorry if I don't kind of name check anybody in particular, but I'm trying to get through as much as we can. One of the things that occurred to me, which is a great question, we have it mostly from Emily here, and they're asking about what are the future breakthroughs, like what are we hoping for? We've had, obviously, JWST seems to have gone up and really just opened up this field spectacularly, is continuing to do so. It's an amazing instrument, and I feel like for the future we've got a lot more coming. But what do you hope to come after that? Obviously we hope it's going to be working for many years to come. What's it going to open up? And that's to any of you really who want to take that question.
I think one of the things I would find interesting, and I've had discussions with people about the possibility of doing this, is, as we all know, biochemistry, terrestrial biochemistry is handed. It's chiral. Amino acids are left-handed, sugars are right-handed. What's the potential of doing remote observations on chirality?
And is that not possible? That's not possible at the moment then?
Not as far as I'm aware.
Okay. But would we be expecting anything different? Because obviously we've seen what meteorites show us, we've seen what comets and asteroids show us. So do you think there's a possibility that it's going to be different elsewhere?
Well, that's the local universe. So it's in the local part of our galaxy. The origins of chirality, no one's quite sure. It does seem to be that it was potentially extraterrestrial, and we know there are processes that are chirally selective in terms of destroying molecules. But fundamentally, from the chemical standpoint, you can build a biochemistry out of left-handed amino acids, right-handed sugars, but equally you could build them a biochemistry out of right-handed amino acids and left-handed sugars. The theoreticians tell us there's no energetic difference between the two. So there's an interesting question there, is somewhere else in our galaxy, do we have mirror image chemistry happening?
Yeah. And then if there's life there, what might that look like? And actually coming on to that idea of aliens, everyone loves to talk about aliens, but you know, it seems like a silly topic, but of course it's not, because we're talking about all these biochemical reactions going on. And one question could come from this of a kind of, are there ways to look for signals that would suggest life-like chemistry elsewhere? Are we looking for that? Are we not at that stage yet? I'm not sure, probably not sure who that question is directly to, probably Serena, but I'm not sure who wants to take that one.
I can try to answer. I mean, it's a big question. I think there are actually a lot of programs out there that look for a different type of signals that may indicate directly or indirectly life. But I think, let me just start with something that you said earlier, and also Martin picked up on. I think what we should start with is not to look for intelligent life. We should start to see whether we can see life in terms of, from a molecular point of view, from a biological point of view. I think that's where really we should start. And to do that, I think we are in a great position now, especially with future missions that will look at the atmospheres of extrasolar planets, because it's the signatures, molecular signatures from not star-forming clouds, which is what we've been talking about during this webinar, but from the atmospheres of other planets in other solar system. That's where really we can get the first handle on whether there is life elsewhere or not. And I think really that's where our efforts should go into looking for biosignatures in the atmospheres of extrasolar planets.
And initially, is it just about looking for water? Do we think water's, I mean, it's often touted as like the most important molecule for life, but we don't know that for sure, do we? It might be that life exists elsewhere using some other kind of molecule, that some other solvent it can survive in. I'm just wondering if there's, a particular molecule we're looking for that we're most excited about when we see it. We often get excited about water, but is there anything else that we're kind of looking on that we think, oh, that's a really exciting chemical we want to see?
I mean, I leave to the chemists to talk about the real molecules. From an astronomical point of view, there are others. Like if we find methane, for example, is also a good, a good indication that there may be some life on that planet. But I'll leave it to Martin and Wendy to talk about bigger things.
Over the summer, I had a very good summer intern working with me and a couple of colleagues on a somewhat unrelated project, essentially looking at the destruction of fluorinated anesthetic molecules. And we got talking about what evidence, what markers might we use actually for intelligent life on a remote planet. And the one conclusion we came to is we should be looking for perhaps CF bonds, because there are no naturally occurring CF containing molecules. CFCs in our own atmosphere, entirely man-made. The halons, again, entirely man-made. We had reasons for making them, and now we're stopping using them, but they're going to persist in the atmosphere for a long, long time, particularly the molecule CF4, which is the simplest of the perfluorinated hydrocarbons. So maybe that's a hint to something we should look for in observations of exoplanets.
I mean, that seems sensible. I guess it's assuming that other complex life has made the same mistakes or done the same experiments that we've done, but who knows?
Yeah.
A really great question, and I've lost the person that's asked this. I'm very sorry, but they've said it's probably for, I'm not sure, Wendy or Serena, any of you maybe. When you identify these molecules, is there any way you can get information about the concentration of the molecules? Because we've seen all these lines, all these different things that you can see. Is the bigger line showing it's a bigger concentration, or how does that work?
So maybe I can start from an observational point of view. So when we see them in space, for sure, it's indeed from the line themselves that we can get an idea of the amount or the abundance of that molecule. So basically, we essentially look at the curve under the line, and through various methods, with a lot of uncertainties, of course, we can obtain the amount of that particular molecule. And it's not as direct as saying, oh, if a line is very strong, then it's very abundant, and if a line is very weak, it's less abundant. Not always, but to a first order of magnitude, I would say that indeed it's a good indication. If a line is very strong, it means that there are a lot of molecules on that part. There are a lot of those molecules out there making that signal so strong. So yes, indeed, this is in space. In the lab, is I'm sure different.
But actually, this is where the lab can help, because the lab can actually measure spectral lines, so for example infrared lines, and look at the strength of the absorption of a particular molecule, because the same amount of water, for example, and the same amount of a molecule, for example like H2S, will not give the same strength of line, just because of the factors that affect how well the light is absorbed. So we can actually get indications in the lab of how strong a certain amount of, or certain number of molecules, strongly a number of molecules will absorb, and that data then helps Serena and her colleagues to actually identify exactly what the abundance of a molecule is. So the laboratory works hand in hand with the observations in these cases.
That's good to know. And we had a question actually about the dust grains. So, and it's a great question, because how do we know that the dust grains you use as your analogues are actually what are found in the interstellar medium or wherever we're looking? Do we have samples of those grains? How do you know that what you're using is actually good?
Well, I mean, we don't have samples of interstellar dust grains. We have samples of cometary dust grains from some of the missions, particularly very recently. There was something that touched down in the desert in the USA a couple of weeks ago, which was some samples from Comet. We have information about meteorites, and so the type of fluffy grain that was in my cartoon is actually a meteoritic fluffy grain, but we can't really go to interstellar space and collect grains. So we know what they are made of because of spectroscopy, and we know that they're not going to be perfectly round and perfectly flat, and we know what meteoritic grains look like. So we have to use our common sense on the basis of that information to tell us what the grains are going to look like.
That makes sense. I just want to end with sort of what's next? What's next for all of you? What are you know, I kind of asked this at the beginning, but what are we hoping to achieve next? I know there's a lot to come back from JWST, and it links into Wendy's work, even though you're looking at the analogues, and Martin and Serena's work. So, you know, what are we hoping for next? What's the next big thing that we're hoping to see? And that's to any of you.
So maybe again, I can start from an observational point of view. We indeed, as you said, we are waiting for more data from the JWST, in the sense that JWST, unfortunately, I apologize, I couldn't show the last 2 slides. The JWST is giving us some amazing, wonderful ice spectra, so the spectra from the icy mantles on top of the grains, exquisite resolution, and it's very hard to interpret them, but we need more of those, because we need a larger sample in order to make up a story of how these ices are formed. But of course, we also still have we have ALMA from the ground, and ALMA is providing us a very, very precise measurements, very zoomed in of the gas from the same clouds from where the JWST is giving us the ices. So I think it's really this marriage between telescopes on the ground that can observe in the submillimeters, and the telescope in space that can observe in the infrared. And so the gas and the dust observed at the same time, in the same place. And that's really what is fantastic about this era just now.
That's amazing, and I'm excited. I feel like it's a very open field now, and it's a lot in the media. So I feel like a lot of people know what JWST is and are learning about it. And I'm hoping that we've got all these young people coming into the field in the future who can have all these new ideas to really kind of progress and find. But I want to say thank you to our wonderful guests today, Martin, Serena, and Wendy, for sharing their knowledge on this exciting field of astrochemistry. It's been absolutely amazing.
Learned a little bit about what's there between the stars in the dust grains. Now we'll close now with a video known as Cosmic Eye. It was from 2018 by this gentleman here, who's flying in, looks like the European Space Agency's equivalent of the NASA Vomit Comet. This is Professor Danail Obreschkow from the University of Western Australia. And a bit more information, a bit more information here. The woman that's actually featured inside this video is Australian cellist Louise McKay. And he actually developed this originally for teaching at the University of Western Australia, an arts class, teaching arts on the scale of things. So this goes from the very big to the very small. And he also developed an app on for the Apple iPhone, an iOS app, and that's called Cosmic Eye. And indeed, if you've got an iPhone, you can actually go and do that. And have a look at some more of the details here. Now, this goes for about 3 minutes, and then we'll close. So it's a wonderful, wonderful video, and a good one to finish with. And a lovely one. Wow. Lovely one to end with. Yeah. Wow, indeed. Wow, indeed. And with that, I'll close the meeting, and hopefully we'll see you all at the May meeting.